Hi, I'm Gary, and I want to show you how I use Cloudy. Okay, in this video, we're going to combine the grid command and save line list, and we're going to save the emissivity of a series of oxygen lines and some hydrogen lines and vary the density over 30 orders of magnitude to see how things change. So let me look at it. Let's look at a input script. Let's go to the top. Okay, so this is our very simple calculation. So it has a title. So we're going to make a model of a cubic centimeter of gas. And then we're going to vary its density over a huge range. So save prefix allows you so you can save files without specifying the main name. So this name, varyn, for changing the density, will be used for all the save files. Now we're going to do this is a homework problem. We're not doing a real physics problem. I want to show you the emissivity of lines as a function of density, critical density, that kind of thing. So we're going to turn off some physics. That'll make Cloudy run a lot faster. So we're going to turn off the energy balance. In a normal Cloudy calculation, you have heat input coming into the gas, mechanical energy, photoionization, something, and that's balanced by cooling, where the heat is converted into light that's emitted. So we're going to turn that off. And we're going to set a constant temperature of 10 to the fourth Kelvin, which is pretty typical of a photoionized cloud. We're trying to do a homework problem, not a full physics problem. And cloudy includes all the physics. And so, in particular, cloudy includes the incident radiation, photoexciting all the levels in an ion. And so, if you just do 1 cubic centimeter of gas, the gas is optically thin, so you end up with a photoexcited cloud. We want to look at only the collisional excitation. So this is a fudge. It's going to turn off induced processes, meaning that there's no photo pumping of levels that will make things a lot simpler. In nature, if a cell of gas is optically thin, if you have a very small column density cloud, it will be photoexcited. And when the cloud gets very big and it has a very large column density, it becomes self-shielded. That means that the pumping lines become optically thick, and so they stop pumping. We're just going to turn that off. Now we're going to vary the hydrogen density. H10 is a log of the hydrogen density. You have to give it a number to get it past the parser, but it's not used for anything. What is used is the keyword vary. Then the next line is the grid command, and that sets the grid point. So we're going to vary the density from 10 to the minus 10 up to 10 to the 20, so it's 30 orders of magnitude. And we're going to take half-dex steps. So 30 orders of magnitude half-dex, you're looking at 60 models or so. We're going to do a unit cell. I mean, this means a cubic centimeter of gas. I use this for testing a lot because a unit cell is the emissivity of the line, which you can find from technical papers. So it's a very convenient way to test the results of the code to make sure it works well against benchmark calculations. So we're just doing one cell of gas, and the thickness is log delta R of 0. So it's 1 centimeter thick. And we'll look at a square centimeter of emission. So that it works out that we're looking at a cubic centimeter of gas. Now, here's some tricks that I'm going to do because I can get away with it. We're not using the temperature solver, and we're setting the ionization in just a bit. So there's a trick you can do to save the number of elements you have to compute. So every element you do takes more memory, more atoms you do takes more memory, and more levels in an atom also takes more memory. So we have a series of initialization files in the data directory. They all end in .ini. And so we have an init command that will read in all the commands that are in the initialization file. If you open this file, what you see is is turning off 29 elements. It's a boring file. So by including this init h-only.ini, I've just now turned off everything except hydrogen. Now, I want oxygen back on, and there's some other things that will be shown in this file. So I'm going to turn nitrogen and sulfur back on. So with these commands, we only have 4 elements to worry about, not the usual 30. That will save time and it will save memory. Next, we're going to turn off the ionization solver. I want to look at O3 lines. And so if you just do a typical model, oxygen may be O6, maybe O1. So in this model, we want O3. So the interpretation here, there's a family of element commands. So you can turn oxygen on or off with element oxygen on off. You can set the ionization of oxygen with element oxygen ionization. The interpretation of the numbers is that they're the log of the ionization fractions. And since we're among friends, you can leave these fractions so they add up to something that's not one. So the interpretation of the element oxygen ionization is 10 to the minus 9 of the oxygen will be atomic. Unity, 100% of the oxygen will be plus, and 100% will be double plus. And then there's no plus 3 because it's not specified. The same for nitrogen. For sulfur, you only have the atom at 10 to the minus 9 of the total, and the first ion is 100%. So these are ionization fractions. The fraction, how much oxygen is in the doubly ionized state divided by the total oxygen. It is a photonization code, so for this case, we would need to set up a radiation field. The code will complain otherwise. It's not going to be used for anything because we've turned off most of these solvers. So this is kind of an O star. It's a black body. And then the ionization parameter we'll talk about a lot later on is a convenient way to specify the brightness of the radiation field for some parameters. And then we're going to save some information. Save grid will save the grid points. So it'll make a table showing us the density of each model. We'll use that for the independent axis of the plot. And then the second of the save line list commands saves the absolute intensity of the line. And so this is going to be in ergs per cubic centimeter per second is the way it's going to work out. And so the interpretation is the contents of this file is a series of lines. We'll look at it next. Will be read in, and Cloudy will work its way through, extract the predictions, and we'll put it into this file. Now, the beginning of the file name is not here. That's because we're using this save prefix. It'll be varyn. So let's have a look at what's in this file, varyn.dat. There's a line list. Whoops. So this is a list of half a dozen lines. So we have two hydrogen lines, H beta and Lyman alpha. So these are electric dipole allowed lines. We have the O3 884 line. Remember, that had a huge Einstein A, Lyman alpha does too. So these are permitted lines. And then we have three classes of forbidden lines. 5007 is a very, very bright. 4363 is a temperature indicator. Then the 88 micron infrared line is from the ground term. So we've got that. So now what we're going to do is run this sim. So I'm going to start it here. Now remember, we're going from 10 to the minus 10 up to 10 to the 20 particles per cubic centimeter in half-deck steps. So we've got a lot of models to compute. So I'll start it here. Let's go over here and start top. So you can see there's a lot of cloudies running. There's a screen full of cloudies. Each one of them, so the name is cloudy.exe, each one of them takes 100 megabytes. So you've got to be very, very careful with the grid command. If you use a large atom, or if you set the continuum resolution very high, you can easily get a lot more memory than this. And so if you can start so many processes that you've used up the system memory. And Macs in particular don't work very well when that happens. So let's let this cook and we'll come back and see what happens. Okay, it's done. First thing I compulsively do is look at the grid file. So we saved the grid. So I'm going to do vary in I called it .grid. It's just my convention. Turn off line wrap. Okay, so this is the output of the grid file. So it gives each one of these lines is a different model. And the first thing you check here is whether the calculation is okay. So the first number is an index for the calculation. The next question is true or false. Is it a failure? Then the third column, all F's here, were there any warnings? And then you go to the fourth column, exit code, okay. So this means the calculation stopped okay. So we can go down and we can see they all stopped okay. Now let's go to the end of the line. These last columns will be used. We're going to read this file in views to make plots. And so this last column out here is the numerical value of the varying parameter. So in this case, we're varying the density. So this is the log of the hydrogen density. If you're varying the stellar temperature, it would be that. You can make nested grid loops where you vary a density and vary temperature of the star or vary ionization. You can vary as much as you want and you'll get these grid points here, which you can then make, say, a 3D Earth surface plot, something like that. Okay, so the next step is to switch gears and go over to views. I'll be back in just a second. Okay, I've opened up views. I've already set up the plot, but let's just look at some high points. Now, what I've done is I've read in the .grid file. I've imported the .grid file, and I'm going to use the column that gives the numerical value of the density for each model. That's going to become the x-axis, the independent axis down here. And then I read in the line abs file. That was from the save line data absolute command, and that gives. At the end of the day, it's going to be the emissivity or the ergs per cubic centimeter per second in that line. And so this is for hydrogen Lyman alpha. So that's an electric dipole transition. So it has a very, very high critical density. The x-axis is from the grid point. So that's 30 orders of magnitude from 10 to the minus 10 to 20 log n. And this is the emissivity. This is a really big scale. Each one of these is many, many orders of magnitude, to 12 orders of magnitude from here to here. So you can see that the emissivity has gone up as n squared, just as it should do. So what I'm going to do then is go down and add other lines to the plot. So now I've added the electric dipole, the permitted O3 line. And it looks a lot like Lyman alpha. They behave somewhat the same way. You can see that the critical density of the O3 line has been hit something like that. It goes over from n squared slope over to a linear slope. So let's go on to the next one. So this is, all right, here we go. This is the O3 5007 line. So it has a much, much lower critical density. So it goes up as the square of the density until it gets to a density of about 10 to the 5. And then it goes over to going up linear in density. So it's often said that forbidden lines are suppressed at high densities. They don't go away. They are still getting brighter. But you'll notice that these permitted lines, the first two, continue to go up as a square of the density. O3, the forbidden line, only goes up linearly with density. So this is now orders of magnitude fainter than the hydrogen lines that were in the spectrum. So it's just a matter of contrast. We don't notice them. So let's go down to add in another line. This is the 4363, the temperature indicator, has a slightly higher critical density than the O3 5007. But then on this scale, they actually merge into a single line. That's because this is 12 orders of magnitude. They're within a factor of a few of one another. And then the last one to look at would be the 88 micron line. That's even more interesting. So what happens now, the critical density for the 88 micron line is the lowest of all, roughly 1,000, as I recall. So it goes up as a square of the density, it's 1,000. Now it's going up linearly in density. Now, cloudy includes all the physics. It does not compromise on microphysics. That's what it does. It's microphysics. So there's a lot of microphysics that comes in at high densities. The high density case is not as simple as you might read in Osterbach or Spitz or something like that. There's a lot of dense plasma effects that come in, and cloudy includes these. It's been applied at very high densities, even for tokamaks. And so the two effects that come in the infrared or radio, first the plasma frequency comes in. As the density goes up, the plasma for an ionized gas, the plasma frequency comes creeping in uh, from the radio is affected first. And then the second thing that comes in, other opacity sources, especially free or Brem's opacity comes in. It goes up as the square of the density. So when the gas gets very, very dense, there are other things that can happen to infrared emission that are unexpected. So there's a lot of cool physics in this. Setting up the sim had a couple of tricky bits. There's a few new commands were introduced. Then I disabled some physics because I wanted to keep it very, very simple. In real calculation, you would leave all the physics alone. You want Cloudy to include all of its physics. But this shows the simple case of a pure collisional model. We turned off induced processes. So it's only a collisional model at a given temperature and a given level of ionization. The only thing varying is the density. And so you can see why it is a very, very dense gas has no forbidden lines. You just can't see them. The forbidden lines go up and overwhelm the whole thing. So we'll go on and talk about other varying things like temperature and stellar parameters in later videos. So see you then.